Space exploration has played a pivotal role in advancing high-precision timekeeping, intertwining the frontiers of astronomy, physics, engineering, and technology in ways that have transformed not only our understanding of the universe, but also practical aspects of modern life on Earth. The demands of space travel, navigation, and communication have driven continuous improvements in the accuracy and stability of timekeeping systems, creating tools that serve as the backbone of satellite navigation, global communication networks, scientific research, and even financial systems. Timekeeping in space contexts goes far beyond the simple measurement of seconds. It involves synchronization across vast distances, accounting for relativistic effects, and designing instruments that can endure extreme conditions while maintaining a level of precision so refined that even nanoseconds matter. The development of atomic clocks, relativistic corrections, satellite constellations, and space-based experiments exemplifies the extent to which exploration beyond our planet has accelerated the march toward perfecting the measurement of time. The relationship between space exploration and timekeeping became especially clear with the launch of satellite navigation systems like GPS, GLONASS, Galileo, and Beidou. Each satellite in these constellations carries multiple highly precise atomic clocks, typically cesium or rubidium, and newer generations are equipped with even more accurate hydrogen maser or optical clocks. These devices are essential because GPS and similar systems fundamentally rely on timing. The calculation of a user's location is determined by measuring the time it takes for signals to travel from satellites to receivers on Earth. An error of even a few nanoseconds can translate into a position error of several meters, highlighting why high-precision timekeeping is indispensable. The act of putting atomic clocks into orbit forced engineers to miniaturize, stabilize, and ruggedize devices that had once been confined to controlled laboratories, accelerating their transition into reliable instruments for global use. The extreme conditions of space, temperature fluctuations, radiation exposure, and isolation from constant maintenance pushed clock technology to become more robust and self-sufficient, developments that in turn have made their way back to Earth applications. Einstein's theories of relativity also entered practical use through space missions and satellite timekeeping. General relativity predicts that clocks run faster in weaker gravitational fields, while special relativity predicts that clocks in motion run slower relative to stationary observers. For satellites orbiting Earth, both effects are significant. The weaker gravity at higher altitudes causes their clocks to tick faster than those on Earth, while their orbital speeds slow them down slightly. The net effect is that satellite clocks advance about 38 microseconds per day faster than clocks on Earth's surface. If uncorrected, this discrepancy would render GPS systems useless within hours. Space exploration forced the direct application of relativistic physics into technology, demonstrating that timekeeping at such precision levels cannot ignore fundamental principles of space-time. The very act of synchronizing clocks across space and Earth required the integration of deep theoretical physics into engineering practices, creating one of the most compelling examples of scientific theory becoming a critical engineering necessity. Advances in atomic clock technology were accelerated by the demands of space missions. Cesium-based clocks, which defined the second as 9,192,631,770 oscillations of the cesium-133 atom, provided the first breakthroughs in high-precision timekeeping. Rubidium clocks, though slightly less stable over the long term, offered greater compactness and robustness, making them suitable for satellites. Hydrogen maser clocks pushed accuracy even further, achieving stability at levels of parts per 10^15, enabling not only better navigation, but also opening possibilities in deep space communication where synchronization across astronomical distances becomes essential. More recently, the development of optical lattice clocks, which use strontium or ytterbium atoms oscillating at optical frequencies, have demonstrated potential accuracies surpassing 1 part in 10^18. These clocks, tested and improved through space missions and satellite-based research, could redefine the second itself and open the door to navigation and measurement systems with unprecedented precision. The role of space exploration here is profound. By providing both the demand and the environment for testing, it ensures that clock technology continues to evolve beyond laboratory prototypes into practical tools. Timekeeping in space exploration is not limited to navigation. It is also essential for deep space communication. Signals sent from spacecraft traveling millions or even billions of kilometers away rely on precise timing to be deciphered. The Deep Space Network, DSN, a global system of antennas that communicate with interplanetary missions, requires atomic clocks with extreme stability to detect faint signals from distant spacecraft. For example, the Voyager probes, now operating in interstellar space, transmit signals that take more than 18 hours to reach Earth. Synchronizing these signals and extracting usable data would be impossible without clocks capable of maintaining stability over such long timescales. This same precision allows scientists to conduct radio science experiments, such as measuring the gravitational fields of planets, probing atmospheres, or even detecting gravitational waves indirectly through timing variations. In this way, high-precision timekeeping not only supports communication, but also becomes a scientific instrument in its own right. Space-based timekeeping has also become a vital tool in geodesy and Earth science. Satellite navigation systems with atomic clocks enable precise measurements of Earth's shape, rotation, and gravitational field. Subtle variations in these parameters, detectable only with nanosecond timing precision, provide insights into tectonic activity, sea level rise, and climate change. Time transfer, the process of synchronizing clocks at different locations through satellites, has enabled global experiments in physics and improved the accuracy of international time standards. The International Bureau of Weights and Measures, BIPM, combines data from atomic clocks worldwide, many of which are synchronized via satellites, to maintain coordinated universal time, UTC. Without the contribution of space technology, achieving global uniformity in timekeeping would be far more challenging. Thus, the impact of space exploration extends not only outward into the cosmos, but also back toward Earth, enhancing our understanding of our own planet. Space exploration has also spurred advancements in portable and autonomous timekeeping systems. Missions to the Moon, Mars, and beyond demand spacecraft that can operate independently for extended periods without relying on Earth-based synchronization. This has driven the development of space-hardened atomic clocks such as NASA's Deep Space Atomic Clock, launched in 2019. This mercury ion-based device demonstrated long-term stability and autonomy, paving the way for spacecraft capable of navigating themselves through the solar system without waiting for time signals from Earth. Such autonomy reduces communication delays and improves mission efficiency, especially for crewed missions where rapid decision-making is critical. Future interplanetary missions will likely depend on networks of spacecraft equipped with advanced clocks, creating navigation and communication systems that extend across the solar system in a manner analogous to GPS on Earth. The precision enabled by space-based timekeeping also intersects with fundamental physics. Experiments with atomic clocks in orbit allow scientists to test aspects of relativity with unprecedented accuracy. By comparing clocks on Earth with those on satellites, researchers can probe gravitational redshift and search for deviations from general relativity, testing the very foundations of modern physics. Optical clocks in space could one day detect tiny variations in the gravitational potential of Earth or other planets, effectively turning timekeeping devices into tools for mapping gravitational fields at extraordinary resolutions. Some proposals even suggest using networks of ultra-precise clocks to detect passing gravitational waves by observing the minute distortions in space-time that alter the synchronization of signals between distant clocks. These concepts illustrate how timekeeping, once seen as a purely practical concern, has become deeply entwined with the exploration of the fundamental nature of the universe. In addition to their scientific roles, high-precision clocks have direct implications for commerce and society. Financial markets, communication networks, and power grids all rely on precise synchronization, often derived from satellite systems originally designed for space exploration. The robustness and availability of accurate time signals have become critical infrastructure for modern economies. As space missions continue to drive improvements in clock technology, these benefits cascade down to everyday life. Portable, low-power, and highly accurate atomic clocks developed for satellites now serve in telecommunications, transportation, and scientific research, illustrating how the needs of space exploration create ripple effects across all sectors of human activity. The vision for the future includes deploying optical lattice clocks into space, where they could serve as the next generation of timekeeping devices for navigation and science. These clocks, with accuracies so refined they could measure the difference in gravitational potential between the tops and bottoms of mountains, would revolutionize both space exploration and Earth observation. Networks of such clocks could create a clock constellation, offering positioning services far more accurate than current GPS, enabling centimeter-level precision globally. On interplanetary scales, they could facilitate autonomous navigation for spacecraft, reduce dependence on Earth-based signals, and open new pathways for deep space exploration. Space missions, by testing and validating these devices in the harsh conditions of orbit, act as proving grounds for technologies that may ultimately reshape global infrastructure. Another frontier lies in quantum timekeeping, which leverages quantum entanglement and superposition to push the boundaries of accuracy even further. Space-based quantum experiments, already underway on satellites like China's Mikius, hint at future systems where entangled particles provide unbreakable communication links and synchronized time signals immune to classical limitations. Such advancements, nurtured by the challenges of space exploration, could transform both scientific research and secure communication systems on Earth. By placing quantum devices in orbit, researchers can conduct experiments not possible in terrestrial laboratories, further intertwining the progress of timekeeping with the expansion of humanity into space. Timekeeping has always been linked to humanity's desire to explore. From ancient civilizations tracking the stars to guide navigation, to modern satellites carrying atomic clocks, the quest to measure time with ever-increasing precision reflects a deeper drive to understand our place in the cosmos. Space exploration amplifies this connection, demanding levels of precision and stability that continually stretch the boundaries of technology and science. The challenges of synchronizing signals across millions of kilometers, compensating for relativistic effects, and operating in hostile environments all serve as catalysts for progress. Each mission, from GPS satellites orbiting Earth to probes at the edge of interstellar space, contributes to refining our ability to measure time, a pursuit as fundamental as exploration itself. In this sense, the role of space exploration in advancing high-precision timekeeping is not just a matter of technology, but also of perspective. By forcing us to reconcile theory with practice, to build instruments that bridge the gap between abstract physics and practical engineering, space missions transform timekeeping into a universal endeavor. The clocks ticking in satellites and spacecraft embody both human ingenuity and the natural laws of the universe, serving as beacons of precision that guide us through space and time. As exploration continues, these instruments will not only support our journeys beyond Earth, but also deepen our understanding of time itself, turning every tick into a testament of how far humanity has come in synchronizing its aspirations with the rhythm of the cosmos.